Hello students, good evening. So we are in the session 11 of ray optics. We're discussing about the refraction through lens, right? So already in the previous class, I think we have come up to the lens equation and how do you find lateral or the transverse magnification for the image, and also we have looked at the power formula. So if you look at the equations, right? So these are the equations that will actually help us in understanding the image formation through the lens. So we'll call them as what? The lens equations. What are those? The equation for finding the position of the image. So 1 by V minus 1 by U is equal to 1 by F, and accordingly the linear magnification, or we can call it as a lateral magnification or transverse magnification, because if this is the axial line, right, then we are looking at magnification which is perpendicular to that, like we hold the object upright. So that's the reason why we call it as what? Lateral magnification. We can also call it as a transverse magnification. Why? Because it is the object is held perpendicular. So magnification formula will be what? It will be height of the image by height of the object. That will be equal to V by U. I think I might have even told you that kind of a mnemonic that we'll use to remember this mirror equations and lens equations together. Because if you see, what is that fundamental difference, right? In case of lens, what do we have? It is 1 by V minus 1 by U is equal to 1 by F. In case of mirror, it will be what? 1 by V plus 1 by U is equal to 1 by F. Here magnification is V by U. In case of mirror, the magnification is what? Minus V by U. So the equation, if minus comes, means magnification will not have minus. Equation minus is not coming means magnification will have minus. So I think I might have told you this mnemonic, triple M. So what is this? Mirror magnification minus will come. Means when the mirror magnification minus is coming, the mirror equation minus will not come. The lens will be exactly reverse of that. Okay, so this is how we can try to remember this in easy method. And the converging ability or the diverging ability of the lens to bring the rays together or to diverge the rays right away is represented by the term called as what? The power of the lens. So power of the lens is measured in terms of diopter. What is it? It's nothing but reciprocal of the focal length. 1 by focal length. If you take the focal length in meter, then the power will be coming in terms of meter inverse. This is what we call as diopter. Okay, so if you have a converging lens, so when we talk about a converging lens, means what is a converging lens? Its focal length will be positive. Parallel beam of rays, they'll go and converge to a point on the right side of the lens. So focal length will be what? Positive. So accordingly power also will be positive. Diverging lens, when we pass a parallel beam of rays, after refraction they will diverge. I mean, the lens that we are marking here is what? Convex lens, which is usually converging. But if you have a diverging lens, which is typically our concave lens, so if you have a concave lens, right, that will be diverging. So for that, if you look at, right, diverging rays, they appear to come from a point over here. Now for the diverging lens, what do we have? The focal length will be negative and hence power also will be negative. So this is what, in short, the equations approach. Okay, now the focal length in case of a mirror, right, we have seen it, we have a relation between the focal length and the radius of curvature. For the mirrors with small aperture, and when we consider the rays coming and incidenting on the mirror to be rays which are close to the principal axis and making a small angle, we will call them as what? Paraxial rays. You take a mirror, right, this is the principal axis. The rays that will come very close to principal axis, we call them as what? paraxial rays. So that is the usual assumption which we'll work with the mirror. So for the assumptions that we have generally considered, right, we have a relation between the focal length and the radius of curvature. What is it? F will be approximately equal to R by 2. This is the relation both for the concave mirror as well as the convex mirror. So whatever is the R, depending on that, the focal length will be approximately decided. But if you want to really find the focal length, means what? You have to pass a parallel beam of rays and see where they converge or from where they appear to diverge from. That is the actual method. But based on the geometrical simplifications, right, we will know in case of mirrors, for the assumptions we consider, F will be approximately equal to R by 2. But here in case of lens, how do we find the focal length? So in case of lens, we will be able to find the focal length from what we call as the lens maker formula. So lens maker formula is nothing but the application of the refraction equation at a spherical boundary. So already we have seen the refraction equation that will happen at a spherical boundary. We are going to simply apply it. So when we apply the refraction equation at a spherical boundary, right, we will be able to get this lens maker formula that will give us the focal length. So for that we will consider an object. So the object is basically producing the light rays. The original light rays, right, will be in the surrounding medium. So we are considering the surrounding medium refractive index as what? Mu s. Then the light rays are getting refracted here at the boundary 1. They will go into the lens. Lens refractive index, we are calling it as what? Mu subscript L. Then again they will undergo refraction, they will come into the outside. So here the assumption that we are going with is, on both sides of the lens we have the same medium. Means this side also, if there is air, means other side also there will be air. If this side there is water, means other side also there will be water, like that. Okay. Now here if you look at the refraction at the first boundary, let us look at the refraction at the first boundary. Okay. So for this spherical boundary, let us call the radius of curvature as R1. We are taking the radius of curvature as what? R1. Now the original rays are in the surrounding medium. After refraction, they are getting into the lens material. Remember the refraction formula in case of the spherical boundary, what is it? Mu2 by V minus mu1 by U is equal to what? Mu2 minus mu1 by R. Correct. So here what is this mu2? The refractness second medium where the rays are entering into. V represents what? The image distance. Mu1 is the refractness of original medium. U is the object distance. R is the radius of curvature. Correct. Now what we'll do is we'll just go as it is. So here after the refraction at the first boundary, let us say the image is formed at point here. Let us call it as what? I1. The distance of this image is what? V1. So here we are going with the assumption of thin lens. Means this T value we will consider it to be very, very small. The thickness of the lens we will take it to be very small. We are going with the thin lens assumption. So the image formed because of the refraction at the first spherical boundary is happening at what? I1. Okay. Now we will apply the refraction equation at the spherical boundary. What is it? After the refraction at the first interface, right, the rays are getting into the lens material. Means mu2 will be what? The lens material refractive index divided by what is the image distance V1 minus mu1. First material is what? The surroundings by object distance is what? U is equal to what? Mu2 means mu of the lens minus mu1, mu of the surroundings divided by R1. Okay, so this is how we are able to get the first refraction equation at the spherical boundary 1. Now we will look at the refraction happening at the spherical boundary 2. So for the refraction happening at the spherical boundary 2, so here what is the object? The image I1 will be now the object for the spherical boundary 2, which means the object distance is what? V1, and after refraction the final image is formed at I. That distance is what you are calling as V. Understand carefully. The image of the first refraction is going to act as the object for the second refraction. Means I1 will be the object for the refraction happening at the boundary 2. Okay. So look at this. Here initially where the rays are, initially the rays are in the lens material. After getting refracted, they are coming onto the outside surrounding. Means here this is mu2 and this is mu1. Let us say the radius of curvature of the second boundary is R2. Now look at this. What will be the equation we'll have? Mu2 by mu2 is what? Surrounding, right? Mu s by final image distance is V minus initial medium is what? Lens material by object distance, as I said, right? It is what? V1. The image of the first refraction will be the object for the second refraction. Again here we are considering that the lens is what? Thin lens. Okay, that's why we are neglecting the thickness value. That is equal to what? Mu2 minus mu1 by R2. So mu2 is what? Here for the second refraction, medium 2 will be the surrounding minus medium 1 will be the lens material divided by R2. So these are the two equations. All that we are doing is just applying that spherical boundary refraction equation two times. First at the surface 1, second at the surface 2. In this, what we are keeping in mind is the image formed due to the refraction at surface 1 is the object for the refraction at the surface 2. That is the only thing. And we have to carefully use that notation when we have the refraction at the spherical boundary equation, right? Mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. We have to take those values as per the convention we follow. Correct. Now look at these two equations. If you can just add both these equations, if you add them, what happens? Look at this LHS. Mu L by V1 minus mu L by V1, that will get cancelled. So LHS is what? Mu S by V minus mu S by U, that is LHS. RHS is what? Mu L minus mu S by R1 plus mu S minus mu L by R2. Now we can see mu S we can take common. 1 by V minus 1 by U will come. Here look at this. No, this is mu L minus mu S. This is what? Mu S minus mu L. So we can write it like what? Minus of mu L minus mu S. Like that we can write. So if you take mu L minus mu S common out, we will be having 1 by R1 minus 1 by R. Divide both sides by the mu S. Mu S is what? Refractive index of surrounding. Divide both sides. What we'll have? This will get cancelled. Okay. So then you can just write down what we are going to get as the final relation. So what will be the final relation here? Left hand side we will be having 1 by V minus 1 by U. I think now we are able to get a hint, right? We are able to get a hint of what is it that we are going to arrive at. So 1 by V minus 1 by U is equal to what? This is mu L minus mu S. When we split it, right, it will be what? Mu L by mu S minus mu S by mu S. So which is what? Mu L by mu S minus 1 into 1 by R1 minus 1 by R. So this is what is the relation we are getting. And if you compare this with our lens equation, what is the lens equation we have? 1 by V minus the lens equation that we are having is what? 1 by V minus 1 by U is equal to 1 by F, right? Which means what? The 1 by F value is what? 1 by F will be equal to what? Mu L by mu S minus 1 into 1 by R1 minus 1 by R2. So this is the formula for the focal length. What is the formula for the focal length? 1 by F is equal to, as it is, you just compare these two equations. So this is what we are getting from the formula, and this is our original lens equation. Compare both of them. In place of 1 by F, what do we have? Mu L by mu S minus 1. So mu L is the refractive index of the lens material. Mu S is what? The surrounding. Minus 1 into 1 by R1 minus 1 by R2. So here we'll have to take care of couple of things. This formula, right, this is what we call as the lens maker's formula for finding the focal length. But when we have this formula, we need to keep certain things in mind, that the assumption of the rays that we consider. So for the lens, right, we are assuming that the rays will be coming very close to the principal axis. We call them as what? Paraxial rays. And all these VU, R1, R2, when we are using these equations, we should be substituting them with the corresponding sign, because what is 1 by F? It is 1 by V minus 1 by U, right? This is what is 1 by F, right, as per the lens equation. So all these quantities, we should substitute them along with the sign. And of course, in the derivation, we have neglected the thickness of the lens, right? Means what? The assumption of thin lens is what we are going with. And the other assumption that we are taking is what? On both sides, this side of the lens as well as this side, the medium is same. That is another assumption that we consider. On both sides, right, we have surrounding medium to be the same. So under these assumptions only, this equation can be used. What is the equation? It gives us what is the focal length of the corresponding lens. What is the focal length formula? 1 by F is equal to what? Mu L. Mu L is what? Refractive index of the lens material, divided by mu S minus 1 into 1 by R1 minus 1 by R2. So here R1 is what? The radius of curvature of the first interface, the one that comes first surface. R2 is the radius of curvature of the second. We have to take those values along with the sign. Along with the sign means what? Generally our objects are kept on the left side, right? So the rays will coming from the left side. Left to right is what we take as the positive. Opposite will be what? Negative. Anything will measure towards the right side will be what? Positive. Anything we measure towards the left side will be what? Negative. Okay. Now the idea of this lens maker formula, right, will actually help us in understanding the behavior of the lenses, in the sense how the lenses will actually be able to behave. So we'll see, with examples, how we can understand the behavior of the lens by using the formula. Because after all, what is it giving us? It is giving us a focal length, right? From focal length, we will be able to know what is the nature of the lens. Okay. Now, for example, if we are having look at this, let us consider all these lenses, right? They are made up of a material whose refractive index is mu. All the lenses. So what are we considering? Biconvex, biconcave, then plano-convex and plano-concave. For all of them, we are considering the lens to be made up of a material whose refractive index is mu. And outside we are assuming there is air. Air means what is the refractive index? 1. Okay. Now let us look at the first one. So here we have all the focal length values that are already derived and kept. We'll just go one by one. Look at this biconvex lens. If you take both the radius of curvature to be same in terms of value, look at this one. The first boundary, right? Center of the sphere will be on the right side. Means R1 will be what? Positive. Whereas the second interface, where is second interface? Further, the center of the sphere will be on the left. So R2 will be what? Negative. So look at this. If they have the same curvature value, right, we have to take R1 to be positive and R2 to be what? Minus R. Now look at the formula. This is the formula, right? So 1 by f is equal to what? Mu length is mu. Surrounding we are saying air, right? So 1. R1 is what? R minus R2 is minus R. So minus minus will become plus. So mu minus 1. 1 by R plus 1 by R is what? 2 by R. That is our 1 by f. Means from here if you take a reciprocal, right? F will be equal to what? R by 2 into mu minus 1. Check it. So it's a kind of a ready-made formula that we can remember. For a biconvex lens with equal curvature, right? What is the focal length formula? R by 2 into mu minus 1. Assuming the lens is kept with either side medium same, which is the air. Okay. Now we will go to the second one. Look at the second one. Like this we can, these results, right? If you are able to remember them, means in competitive examination that can help us in getting the answers quick. Okay. So look at this one. Second is what? Plano-convex. So plano means what? For a plane surface, right? If you think about a sphere, how big the sphere should be? Infinitely large sphere, right? Because the curvature is not there. Means whenever we have a plane surface, right? For the plane surface, radius of curvature we have to take it as what? Infinity. So here R1 will be infinity. Look at this R2. That will be measured to the left side. So R2 will be what? Minus R. Again we will go with the formula. Mu L, lens is mu, surrounding is air. 1 by R1 means what? 1 by infinity. Minus of 1 by infinity means 0. Minus minus will become plus. So 1 by f is equal to what? Mu minus 1 by r. Means from here we will get f is equal to what? R by mu minus 1. So for a plano convex, what is it? F will be equal to what? R by mu minus 1. Now we will go to the biconcave. So if you look at a biconcave, right? For the first spherical boundary, we have to measure the radius of curvature to the left side. So hence R1 will be negative. What about the R2? R2 will be positive. So we are taking the curvature to be equal. So R1 is minus R, R2 will be plus R. Now look at the formula. R1 is what? R2 is plus. So what do we get? Mu minus 1. That is our 1 by f. Means from here what is the f value? Minus R by 2 into mu minus 1. We can see the formula is exactly minus will come. Whatever we have for the biconvex, we will just have a minus. Now let us try the last one. So all these are some standard results. If you are able to remember them, means it will help you. Otherwise, if you are able to remember the approach, means that is well and good. Whatever is required, you will be able to derive it. Now look at this. Plano concave means first is plane. First is what? Plane. Means R1 is what? Infinity. Plano concave. Okay. Means here R2 will be what? Positive. Look at the formula. 1 by f is equal to what? Here we will have mu minus 1 into 1 by infinity minus 1 by r. 1 by infinity is 0. So we will have what? Mu minus 1 divided by minus r. So f will be equal to what? Minus r by mu minus 1. You can see this is also what? Just negative of our plano convex. Okay. So this is how for any lens that is given to us of, because in the session 10 also we have seen different type of lenses that can be created. Mainly we will focus on our biconvex and biconcave, but you can have lens of any type of curvature and combination given. For that you will be able to find what is the corresponding focal length from this particular formula. Okay, so we will just have to be careful about the sign convention, like whether we will take the radius of curvature to be positive value or negative value. That sign convention part we have to be careful. Okay, so this is about the approach that we need to take to find the refract I mean the refract index of the lens material, the radius of curvatures, relation to the focal length of the lens. Okay, now we'll just take some questions on this. Look at this one. This is a very interesting question. So this is what I told you, right? Generally, what is the convex lens? We'll take it as what? Converging lens, right? A convex lens will be what? Converging. A concave lens will be what? Diverging. But look at the question. A convex lens can act as a diverging lens when? They're asking when the convex lens can act as a diverging lens. Maybe you can type your responses. So when it can act as a diverging lens, think about it. See, we have the formula, right? So if you have the lens which is of a refractive index mu2 and outside medium is a refractive index mu1. So either you will take mu L and mu S, or you take mu2 and mu1. So this is the formula for the focal length, right? 1 by f is equal to what? Mu2 by mu1. Mu2 is what? Lens. Mu1 is surrounding. Minus 1 into 1 by r1 minus 1 by r2. Already we discussed about the convex lens. Look at, this is the first boundary, right? So r1 will be what? Plus r, and r2 will be minus r if you take the convex lens of equal curvature. So look at this. 1 by f is equal to, this is what? Mu2 by mu1 minus 1 into, this is 1 by r minus 1 by minus r. Okay, so what is this? 1 by f is equal to mu2 by mu1 minus 1 into 2 by r. Now we are looking for, see, the diverging lens concept means what? We need to have focal length to be negative. Diverging lens concept means what? Focal length should be negative. So look at this formula and tell me when the focal length can actually be negative. Focal length will be negative when mu2 by mu1, right, is less than 1. Which means what? Mu2 is less than mu1. Mu2 less than mu1 means what? The refractive index of the lens material should be lesser than the refractive index of the surroundings. Means if you take the lens and go and keep it inside some medium, oil or something, where the refractive index of the surrounding is actually higher. Normally if you have a convex lens, keep this in air or even keep this in water, then the convex lens will still act as a converging lens only, because the water refractive index is also lesser than the glass. But if you go and keep this lens in some other medium where the surrounding refractive index is higher, then in that case what we will be having? The focal length will be coming as negative, which means in those cases, right, the so-called converging lens, generally, whenever we use the word convex lens, we will think of it like what? A converging lens. The so-called converging lens will then act as what? It will be acting as an diverging lens. Okay, and just since we are discussing this question, right, let us discuss couple of more ideas. What if we have a lens? We are having imagine we have a convex lens. The refractive index of the lens material is same as the outside medium. Means what? Mu2 is equal to mu1, which means this will be 1, right? So 1 minus 1 into 1 by r1. So 1 minus 1 means what? 0, which means f will be coming as what? Infinity. The focal length is what? Infinity. So means what would happen? The rays would just go through. So for any lens, right, when we say the focal length is infinity, means what? When a parallel beam of rays are coming, they will converge to a point infinity. Means what? They are not converging, they are simply going as it is, right? When we pass beam of rays, means they will pass as it is. So if you take a lens and keep this in a medium where the refractive index of the lens is same as the refractive index of the medium, it is like what? Just the lens is becoming a part of the medium, that's it, right? Both have the same refractive index. The light rays will just go as it is. There will be no concept of refraction at all. Okay, so that will happen when the refractive index of the lens material is same as the refractive index of the surrounding. Okay, now here we talked about a convex lens acting as a diverging lens. Now the same thing can be asked in other way also. When a concave lens can act as a converging. When a concave lens can act as a converging. For that also same concept, right? When a concave lens will act as a converging, when we keep the concave in a medium which is having a higher refractive index than the lens material. Okay, so in case of the concave, what we see is R1 is negative, R2 is positive. So what is the formula? 1 by F is equal to what? Mu2 by mu1, 1 by R1 minus 1 by R2. So what is this? Minus 2 by R. Okay, now if you look at the outside medium having a higher refractive index, if mu1 is more than mu2, right, means what? Mu2 by mu1 will be less than 1. So this term also will be negative. Second term already is negative. Negative becomes what? Positive. So as a result, we will get the focal length to be what? Positive. So a concave lens can act as a converging lens. A convex lens can act as a diverging lens when we keep the lens in a medium whose refractive index is higher than the lens material. Okay, so it's a very important reasoning question. Like the way in case of mirrors we had, right? We have asked about when a concave mirror will okay, so in case of mirrors, right? So we have the question of when convex mirror generally forms what? It will be forming virtual images. So we had the question when a convex mirror will be able to form a real image. When it will be able to form a real image? When the object is virtual. So I hope you guys remember that particular question. So these kind of reasoning questions we have to keep a note of it. Okay, so this is about how we will try to understand the changing behavior of the lens. It's not like, it is only about the lens material. The behavior of the lens depends upon what is outside. It depends upon what is the outside medium also. Okay, now look at this one. These kind of questions are pretty common when it comes to medical entrance examination. Look at this one. Focal length of a convex lens in air is 10 centimeter. Find its focal length in water. Means for a convex lens in air, what is the focal length? 10 centimeter. We have to find the focal length in the water. What is given to us? The refractive index of the glass is what? 3 by 2. And refractive index of water is what? 4 by 3. So look at this. So here we are keeping the lens in the air. Then we are keeping the lens in the water. So here what is the lens material? 3 by 2. Here outside is what? 1. If the outside is water, means outside what is the refractive index? 4 by 3. Correct. Now what is the formula we have? Assuming it is a convex lens of equal curvature, right? What is the formula? I hope you guys remember the formula, right? What is it? We have the F is equal to what? R by 2 into mu minus 1 for the convex lens of equal curvature, right? What is the formula for the focal length? F is equal to what? R by 2 into mu minus 1. So here mu is what? Mu means refractive index of the glass by refractive index of the air. So look at this, R by 2 into mu means what here? 3 by 2 minus 1. 3 by 2 is what? Half. Half into 2 is 1. So F is equal to R. What is the F? When we are keeping in the air, what is the F value given to us? 10 centimeter. In the second case, right, let us call it as F dash. F dash will be equal to what? R by 2 into, here we will call it as mu dash minus 1. So mu dash will be what, you know? Refractive index of the glass by refractive index of water, which is what? 3 by 2 divided by 4 by 3. So what is it? 3 will go to the numerator. It will be what? 9 by 8. So look at this. R is already 10 centimeter. 9 by 8 minus 1. What is 9 by 8 minus 1 means? 1 by 8. Okay. So F dash will be equal to what? 10 centimeter. 2 into 1 by 8. 2 ones are 2 4s are. 4 will go to the numerator. 4 tens are what? 40 centimeter. That is our F dash. So I told you, right? If you remember that result, it will actually help you to get the answers fast. What is the focal length of the lens when we are keeping it in water? Check it up, guys. What is the answer for this? It is what? 40 centimeter. When we keep the lens in water, the focal length value will be what? It will become 40 centimeters. So all we are doing is we are just going back to that formula. So if you have mu and outside is air, what is the formula for the focal length? R by 2 into mu minus 1, right? Here mu, if you have outside some other material, means in place of mu, what we have to take? Refractive index of the lens by refractive index of the surrounding. We have to take the relative refractive index of the lens material with respect to the surrounding. Okay, so this is the way in which when we change the outside medium, the focal length will change. Same convex lens. When we keep it in the air, the focal length is what? 10 centimeter. When we keep it in water, focal length is becoming what? 40 centimeter. Remember, when the focal length changes, power, the converging power of the lens also will change. Convex lens means we'll talk about converging power, right? Converging power of the lens also will be changing. Okay. Look at this one. So these kind of questions, right, we need to be very comfortable. So all these are the questions based on the lens maker formula. Find focal length of the system shown in the figure from left hand side. Okay, so why are they sometimes say this? Take it from left hand side. Why? Because when we take it from left hand side, this is our surface 1, this is our surface 2. The left hand side is what? Surface 1. Right hand side will be what? Surface 2. Okay. Now look at this. How do we proceed? The mu2 value, which is the lens material, what is it? 1.5. They have given everything. Mu1 outside, both the left side as well as right side, what is it? 2. R is what? Look at this. First curvature is spherical. It will be what? Center will be on the right side, right? Which means what? This will be taken positive. Second surface is what? Plane surface. Means R1 is 40. What about R2? Plane surface means infinity, right? Plane surface means what is it? Infinity. Now let us see what is the formula we have. 1 by F is equal to what? Mu2 by mu1. Mu2 means what? Lens material. Okay. Mu1 means what? Outside. Mu2 by mu1 minus 1 into 1 by R1 minus 1 by R2. Okay. So we'll just have to substitute. Mu2 is what? Lens material 1.5. Mu1 is outside medium 2. Minus 1 into 1 by R1. Remember, R1 is already positive. So 1 by plus 40. R2 is what? Infinity. So 1 by infinity means anyway 0. Okay. So check it. What is the answer we should get? Check it, what must be the answer? So here look at it. Is 1 by f is equal to what? 1.5 means 3 by 2. So 3 by 2, already there is a 2 here. So 3 by 4. What is the 3 by 4? Minus 1 means minus 1 by 4. This is what? Minus 1 by 160. This is 1 by f. Means f will be equal to what? Minus 160. Unit will be centimeter. Why? Because the R1 is in centimeters. R1 is in centimeters. So f also will be coming in terms of the centimeter. So here the only thing is we have to be careful about the sign convention part. So you can see here the first spherical curvature, right? That R1 will be what? Plus, because we are measuring to the right side. R2 is infinity, because whenever we have a plane surface means what? Its radius of curvature is what? Infinity, because plane surface, how much bigger sphere we have to assume? Infinitely large sphere, right? That is why radius of curvature will be what? Infinity. Okay, so this is how you have to check it up, guys, whether you are able to get this answer or not. What is the value of f? So value of f must be what? It should be minus 160. Okay, so we'll move on to the next question. Let us see who can solve this one. Calculate the focal length of the biconvex lens which is kept in the air. Means outside is what? Air. If the radii of its surfaces are 60 and 15, means look at this, we have to take along with the convention. First surface is what? Value 60, but we have to take along with the sign. R1 will measure to the right side, means R1 is equal to what? Plus 60. What about the R2 second surface? Second surface, right? Look at this second surface. So if we extend the sphere, where the center will be? Center will be lying on the left side. So R2 we have to measure to the left side. So R2 will be what? Negative. Minus 15. Okay. Mu of that lens is what? 1.5. Mu of the surrounding is what? 1. Okay. Mu of the lens or the glass is what? 1.5, and the surrounding is air, means 1. So we have to find the focal length. So formula, right? What is it? 1 by f is equal to mu of the lens. What is mu of the lens? Means 1.5. Mu of the surrounding means air. 1 by 60 minus 1 by minus 15. So what is this? This is 1.5 minus 1 means 0.5. 1 by 60 minus minus will become plus. 0.5 means we can take it 1 by 2. This is all 1 by f. Here LCM is what? 60. Okay, so we'll have 1 plus 4. 1 plus 4 means 5. 5 ones are, 5 12s are. So what is it? F will be equal to what? 1 by f is 1 by 24. So f will be equal to what? See, here the sign also matters. So in some other question we are getting f negative. So here we are getting f is what? 1 by f is coming as 1 by 24, means f will be plus 24 centimeters. Why centimeter? Because R1 we are taking centimeter, R2 also we are taking centimeter. So check it up, guys. What must be the value of f? F should be coming as what? Plus 24 centimeters. See, these kind of questions you should be thorough. Any question which is along these lines, right? We should be able to straight away answer them. Look at this one. So this is a question based on the lens equation and the magnification. So what is the lens equation? 1 by v minus 1 by u is equal to 1 by f. Magnification. Magnification means we are talking about the linear magnification. What is it? It will be v by u. Find distance of the image, means they are asking us to straight away find what is v from a convex lens. Focal length 20 centimeter. Remember, generally when they say convex lens, right, we will have to take the focal length to be what? Positive. So here f will be taken as what? Plus 20 centimeter. if the object is placed at a distance of 30 centimeter from the lens, so where do we keep our objects? Always our objects will be kept on the left side. Means u will be what? Minus 30 centimeter. Convex lens, so focal length is positive. Object will be always kept on the left side, so u will be what? Negative. And we have to find first v value. Then they are asking us to find the magnification. So how do we find, what is the formula? 1 by v minus 1 by u is equal to 1 by f. So 1 by v is equal to what? 1 by f plus 1 by u. So 1 by 20 plus 1 by minus 30. What is the LCM? 60. Okay, so 3 minus 2. So 1 by v is equal to what? 1 by 60 means v is equal to what? 60 centimeters. V will be coming as what? 60 centimeters. It's coming positive, means where the image is formed on the right side. The image will be formed on the right side, right? How much distance? 60 centimeters. So check it out, guys. We should be what? 60, or we should say plus 60. Then the magnification. What is the magnification formula? It's a straight formula, right? V by u. V is what? Plus 60. U is what? We have to take along with the sign. U is what? Minus 30. Means magnification is what? Minus 2. What is the magnification? Minus 2. Remember, from the magnification we can conclude a lot of things. What is it? Magnification minus 2 means the image will be what? Inverted. Magnification negative value means what? Image is inverted. And look at the magnification value alone, 2, more than 1. Means it will be what? Enlarged. The image will be inverted but enlarged. Okay. So using the magnification factor we can conclude the characteristics of the image form. Not only the characteristics of the image form, using this magnification factor, right? Like generally they will give us the magnification factor. Remember, we did this in the case of the mirrors also. Looking at the magnification value, right, we can conclude not only the image characteristics but also what is the nature of the lens, and according to that where the object should be placed with respect to the lens. All these things we can conclude by looking at the magnification factor value. So remember, we have did a similar thing in the case of the mirrors also. See here, when we normally analyze, right, we are thinking about either the convex lens or the concave lens. Okay, these are the two types of lenses that we are generally thinking about. So here we have a different set of magnification values. Based on the magnification, right, we will be able to conclude what will be the nature and characteristics of the image. We can even tell what is the type of lens, and for that image to be formed, where the object must have been kept. For that image to be formed, where the object must have been kept. So we'll just look at these values. Now look at the first one. Magnification value is minus 3, means what? The image should be inverted. Minus means inverted. It should be what? Magnified, because the value is more than 1. Negative sign is there but value is more than 1. Now inverted and magnified, that will happen in which case? It will be happening in the case of the convex lens. We have convex lens, right? We will get inverted and magnified image, which will be a real image formed. When for the convex lens, if you have the object placed between f1 and 2f1, remember, for the convex lens, right, focal length 2 will be on the right side. That is what is the focal length that we generally consider. Focal point 1 and focal length 1, they will be measured to the left side. Okay, where we should keep the object between 2f1 and f1. If we keep it there, right, then the image will be formed on the right side of the lens. The lens is what? Convex lens. Okay, the image characteristics will be what? Real, inverted and then magnified. If you have magnification minus 1, this also will come only in the case of the convex. magnification -1, right? It comes in the case of convex when we exactly keep the object at 2f1, image will be formed at the 2f2. It will be what? Inverted. Minus is there means inverted. Same size and real. Okay. Now if you have the magnification, say for example -1/2, so here we have to see the value is less than 1. Sign is negative. Negative means what? Inverted. So we have an inverted diminished. See, inverted diminished will again come in the case of convex when we keep our object beyond 2f1. When the object is kept beyond 2f1, right, means we'll say 2f1 and minus infinity. This side, left side infinity, we call as minus. Right side infinity, we call it as what? Plus. So beyond 2f1, if you keep the object, right, where the image will be formed, it will be formed between f2 and 2f2 on the right side. It will be what? Inverted, real and diminished. Now if you have the magnification +2, it will be what? Erect, magnified. So erect magnified image will come in which case? In the case of the convex, when our object is placed between the optical center, either we will represent the optical center by P or O, whichever rotation we follow. Okay, optical center and f1. So optical center, either we will indicate this with P or O and f1. If you keep the object there, means image will be what? Erect. It will be a virtual image. Erect, virtual and magnified. What is the lens here again? Convex. Now for the concave, we have a general case. We don't have so many cases, right? Concave, we will be forming what? Virtual and diminished. That is what we have to remember. Concave lens means what? Virtual and diminished. So we see here magnification +1/4. Value is positive. Okay. Erect. It will be diminished and virtual. So anywhere we keep, right, wherever we keep the object, we will get what? Virtual, erect and diminished image being formed, and that will happen because of the concave lens. So by looking at the magnification factor values, we will be able to conclude what is the characteristics of the image. Not only that, we will be also able to tell what is the corresponding lens being used, and with respect to that lens, where the object should have been placed. All this we will be able to conclude by looking at the magnification. And both in the case of the mirror also we did this, lens also we did this. I'm telling you again, this kind of analysis, right, will be useful for questions at the JEE mains level and the NEET level. Like they can give us the magnification factor formed by a particular lens is say for example +1/4. What is the lens being used and what is the position of the, like they can ask about the characteristics, either the image characteristics or the position of the object. Okay, so this is what is the information we have stored in the magnification factor value. Now we talked about the linear magnification, or what we call as the lateral magnification. There is one more word for this. What is it? Transverse magnification. That is what we were giving by the formula, right? Magnification is equal to what? V/U. We also have a concept called as axial or longitudinal magnification. What is this axial or longitudinal? Think about it. You have a lens. For example, I am taking a convex lens. It may be a concave lens also. If you keep the object along the axial line, if you keep the object along the axial line, okay, so we have two ends of the object, A and B. So this is the length of the object. Now for A, let us consider the image. Maybe somewhere it is formed. The distance of that corresponding image A dash will be what? V1. For B, we'll measure the object distance to be U2. The corresponding image is formed somewhere. the distance is v2. So here the longitudinal magnification or the axial magnification, right, is about what? The length of the image, because we are keeping the object on the axis. It is what? Length of the image by length of the object. So length of the image means what? Look at this. It will be what? v2 minus v1. Length of the image will be what? v2 minus v1 divided by what is the length of the object? u2 minus u1. So we are looking at what? The length which is measured along the principal axis. So whenever we have a extended body which is kept on the principal axis, what do? We'll have to mark both the ends of that extended body. Look at the image formed for one end. Look at the image formed for the other end. Then the gap between them, right, that a dash b dash. This a dash b dash is what? This is the length of the image. AB is what? Length of the object. We are keeping the object on the axis. So this magnification, right, is called as what? The longitudinal magnification or the axial magnification. What do we call it as? Longitudinal magnification or the axial magnification. Okay. Now this is when the object is of significant size. They'll say, the lens, focal length, say for example, is in terms of centimeters. The object size is also in terms of centimeter. In that case, we have to use this approach. We have to take the image of one end, image of other end, measure what is the gap between those two images. Like you have to measure the gap between a dash b dash. That a dash b dash length divided by ab length. That is what we generally call as what? The axial magnification or the longitudinal magnification. Sometimes they can ask what is the length of the image, like that. Sometimes they can ask us what is the axial magnification or longitudinal magnification. But in this only we can have one more situation, that is the object size may be small. The object size may be small in comparison to the lens parameters. Means the lens focal length is in centimeter. The object size is in millimeter, like that. So dimensions of that object are small. In that case, what we will do is we will have a formula that will come from the differential approach. So where this formula will come? It will come from the differential approach. What is the differential approach? We have the lens equation. What is it? 1 by v minus 1 by u is equal to 1 by f. Just take a derivative of this. Take a derivative of this means what? Take a derivative of this, both the left side as well as the right side, right? So derivative of this will be what? This will be what? Minus 1 by v square into dv. This will be what? Minus 1 by u square into du is equal to, right side it is constant. So derivative means what? It will be 0. Now we'll this is what? Minus into minus will be plus. We'll take the negative term to the right side. So what do we have? 1 by u square into du, that is equal to 1 by v square into dv. Now we are looking for what? Take the du to the that side. V square will come here. So v square by u square, that is what? dv by du. So what is the relation we have? dv by du is what? V square by u square. By the way, v square by u square is what? We have a relation for the v and u, right? This is what? The v by u is what? It is the linear magnification. Okay. So dv by du, if the object is very small, right? Whatever the position of the object, from there if you consider a small change, that is du. Whatever the position of the image we will get, from that we will consider a small change, that is dv. So what is the dv by du value equal to? It is what? V square by u square. So this is the axial or longitudinal magnification formula when the object size is very small in comparison to the lens parameters. So this is what we are getting from the differential approach. So the dv will take it as the size of the image, du will take it as the size of the object. So dv by du is equal to what? Numerically it is equal to what? V square by u square. Okay, that is how we will be able to get what is the axial or longitudinal magnification when the object parameters are very small. General case, this is the formula. We will have to get both the ends of the object. We have to find the images, measure the distance between the end point images, that is like our a dash b dash. So a dash b dash length by ab length, that is our normal formula. But if the object size is very small in comparison to the lens parameters, then we can use this differential formula also. Okay, so this is about the axial or longitudinal magnification. We have seen the same concept in the case of the mirror also. So if you recall it, right, it is like a kind of repetition. Whatever we have seen in the case of mirror, right, we will be seeing all those things again in the case of lens also. The only difference will be the sign value here and there might change because of the difference in the mirror equation and the lens equation. Okay, so in the next class we'll continue our discussion on this, and probably we'll be able to conclude about the lenses with the next class, and after that we'll get into the optical instruments. Okay, we'll see you in the next class.